Hi everyone, welcome to the session on digital design with Verilog HDL. In this session, I am going to discuss about data flow modeling. So these are the contents of the session. First, I will discuss what is data flow modeling. Then I will discuss what is the uses of assign statement in data flow modeling, which is one of the basic statement that is required to assign some values on the nets or registers on data flow modeling. Then we will move to how to give delays in data flow modeling. We have already seen how to give delays in gate level modeling, but in this session we will see how to give the delays in data flow modeling. Then we will go to expressions, operators and operands that are available in data flow modeling. Then what are the different types of operators, and we will see what is its order of precedence. Finally, we will see some of the examples of data flow modeling like multiplexer and full adder. We have already seen this table, right? The different types of data flow modeling. So for small circuits, the gate level modeling approach works very well. But as the circuit complexity increases, the gate level modeling is no longer useful for the designers, because in gate level modeling, we have to design the circuit by using logic primitives that are available in Verilog. If the circuit is very small, let's say if just it is a 4:1 multiplexer or like this, then it is very easy to define this in terms of logic gates, right? But if the circuit is very big, let's say it is a 10:1024 decoder. That means you have 10 address lines and you want to decode 1024 outputs from it. In this case, you will require 1024 gates at the output, AND gates at the output to get 1024 outputs. So writing this many logic gates in Verilog is not feasible. So what designers will do, they will go for either data flow modeling or behavioral modeling. So the term RTL, register transfer logic, will correspond to the coding of Verilog in either data flow modeling or behavioral modeling. So in behavioral or data flow modeling, the designers will design the design by thinking of its functionality, not in terms of logic gates. So if you have a design that needs to be designed, you have to think what is its functionality. Once your functionality is fixed, then you start writing the code for this design. So let's see what is data flow modeling. A data flow modeling is uh, a kind of modeling that is available in Verilog, which defines the data flow between registers and how a design processes the data. This is the main functionality of data flow modeling. What is the use of logic synthesis tool for this data flow modeling? In data flow modeling, we will directly write the functionality of the design, right? Let's say you want to design a full adder. Your functionality is your sum should be equal to A plus B plus Cn, right? Your sum output should be equal to A plus B plus Cn. This is the functionality. As you can see here, we are not using any logic gates. We are directly, we are directly, we are not using any logic gates. There are no logic gates involved. We are directly writing the functionality of your output. In this case, once you write the functionality, this is called RTL, register transfer level. After you write the RTL code, you will use a tool called logic synthesis. That tool will convert your RTL into gate level netlist. The tool will convert your RTL into gate level netlist. What does this mean is, here the RTL means you have written the output in terms of expression, or you call it as a functionality. Once the expression is written, you give it to a tool called logic synthesis. There are various logic synthesis tools that are available. For example, the Synopsys DC compiler is a logic synthesis tool. DC compiler, or even the Xilinx Vivado tool itself has a Xilinx Vivado tool is also a kind of logic synthesis tool, because once you wrote your design source, if you press the button of run synthesis, it will do the synthesis. Synthesis means it will convert the RTL to gate level netlist. So what does it do? It will convert this expression into logic gates that are required to obtain the output. Now let's see what is the uses of assign statement. First of all, what is an assign statement? If you want to have output on any net or wire in data flow modeling, you have to use this statement called assign. The keyword is assign. So what is the syntax of this assign statement? Its syntax is like this: assign its drive strength. If you want to specify the drive strength, you can specify the drive strength, and then if you want to specify the delay, you can specify the delay, and list of arguments or list of net assignments. This is the syntax of assign statement. Basically, there are three types you can use the assign statements. One is continuous assignment, second one is implicit continuous assignment, and third one is implicit net declaration. We will see one by one. In continuous assignment, the left side is always a net. Not in continuous assignment, in any assignment, the characteristics of assign statement is the left side should always be n net. So what I mean is, if you want to assign, let's say assign ASSIGN, this is the assign keyword. Let's say assign A is equals to B and C. So this A should always be a net. Net means we know how to define net, a wire. You need to use a wire A. And B and C can be anything. It can be any data type, like it can be a net or register or vector of net or register or even function calls also, right? The right hand side can be a reg, net or even function calls. I will give you an example for this. So consider this thing: if you are having a continuous assignment statement, the left side should always be a net, and the property of continuous assignment is, once you assign the statement, what does it do? If there is any change in inputs, immediately it will affect the output A. So that means the continuous assignment is always active, which means if there is any change in the right side parameters, right side inputs, immediately the left side output will be affected. So we call this as always driven. So the output is always driven. That is the reason why we should use the output as a wire, because we know wire is the data type that allows always driven outputs, but not the register. In case of register, you cannot have always driven property. That's why we will use the wire as a data type for the assign statement, left hand side of the assign statement. Okay. And you can specify the delays. I will discuss how to specify the delays. Just like we have specified delays in gate level modeling, you can even specify delays in this data flow modeling as well. So let's take 2-3 examples of this continuous assignment statement. This is one of the example, and let's say I want to use assign statement with vectors. So how to do that? I can assign my new address of, let's say, 8-bit is equals to my old address 1 of 8-bit XOR, this is an XOR operator, I will explain in next slide, XOR address 2 of 8-bit. So in this case, this address 1 and address 2 can be either register or net, but this new address should definitely be a net. Net means the data type is wire. So this thing should be clear. The left hand side should always be a net or wire, and the right hand side can be either net or register. It depends on your functionality. One more example, let's see how to use concatenation operation inside the net. So if I want to assign my carry out and sum at the same time, I can define like this. I will explain what is this concatenation operator, but as of now, think that we have a flexibility that you can assign two operands at the same time like this: a of 3 down to 0 plus b of 3 down to 0 plus c of 3 down to 0. I will explain this in coming slide. I don't want c 3 down to 0. I can have c in anything. Whatever you want, you can assign here. So this is called continuous assignment. Now let's see what is implicit continuous assignment. The name itself is suggesting implicit means the place where it is residing, right? So implicit of declaring a net and then writing a continuous assignment on the net. So what I mean is you can define the net as well as you can write the net there itself like this. The example of implicit continuous assignment is you can define wire out is equals to in 1 and in 2 and in 3. So what does this do is it will perform AND operation between in 1 and in 2 and in 3, and it will give the result in out. See, I have defined the wire in the assign statement itself. If I define like this, I don't need to again write the assign keyword. That is the advantage of implicit continuous assignment. Directly define the net and then write the expression whatever you want on this net. So this is equivalent to defining like this wire out. First you are defining and then you are assigning out is equals to in 1 and in 2 and in 3, right? Instead of writing these two statements, you can write a single statement. This is implicit continuous assignment. Now let's see what is implicit net declaration. What does this mean is you don't need to declare the net also. You can directly assign and the Verilog will convert the assigned variable to a net data type, because as I already told, the characteristics of assign statement is the left hand side is always a net. So let's take an example. Let's take my two wires I1 and I2 are my inputs, and I am assign my out is equals to I1 plus I2. So what does this mean? The output is a wire data type. I don't need to specifically write wire out before assigning, because the implicit net declaration will have a flexibility of converting the output to a wire data type. So you don't need to write this extra line. Directly assign out is equals to in 1 I1 plus I2. That will assign the out as a data type of wire. Okay. Now we have seen three different ways of assigning the net or wire. Now let's see how to give delays in data flow modeling. We have already learned how to give delays in gate level modeling, right? In gate level modeling, we can give the delays to logic gates by using hash and then defining how much delay you want. Let's say 5 nanoseconds or 50 nanoseconds. How much time units delay you want, you can define by using hash followed by the number. In the same way, you can give delays in data flow modeling as well. There are three ways you can use the delays. One is regular assignment and regular assignment delay, and second one is implicit continuous assignment delay, and third one is net declaration delay. We'll see what are these three things. In the regular assignment delay, we have a property called inertial delay. What I mean is, let's say you want to assign a delay to the output, of, let's say, 5 nanosecond. Delay to the output 5 nanosecond for input 1 plus input 2. So what does this do? It will evaluate this expression after 5 nanoseconds. So how does this happen? Basically, when you write yep, basically when you write this expression in Verilog, the Verilog will follow the following steps. First, it will check the inputs. If there is any change in inputs, then it will see if there is any delay inside the statement. If there is a delay, then it will wait for this particular amount time of delay before actually calculating this expression and putting the result in the output variable. So in this case, first step is it will wait for change in inputs. Once there is change in inputs, the next step is it will check for this delay statement. If there is a delay statement, if there is delay, then it will wait for that much amount of time and it won't allow any output in that particular time. After waiting for that much amount of delay, then in step 3, it will assign whatever the values that are present at that particular time period. It will do the calculation at that particular time period, and then it will assign the output to this variable called out. This is very, very important. If you don't understand this thing, your output may corrupt, or your output may not be what you desire. We'll see with an example what is this. This property is called inertial delay, and one feature that it has, you cannot say feature, one thing that it has is, if the input pulse is shorter than delay, what will happen? Because as I am saying, it will follow these 3 steps. First step is it will wait for changes, and then next step is it will wait for this much amount of time delay, and third step is it will assign the output. But what if meanwhile it is waiting for that much amount? Let's say if I give the amount of delay is 50,000 nanoseconds. Meanwhile, my inputs are changing; they are not constant. So what what is the output at that time? Whether it will calculate the output based on the time that they have changed, or based on the time that they are assigned. So we'll see this thing with an example. So let's take an example of like this. We'll see with their corresponding time periods. Let's say my assign statement is assign my out. Need to give delay also, don't forget. Assign, give a delay of, let's say, 10 nanosecond, and out is equals to in 1 and in 2. So what I want is, I want to perform in 1 and in 2 and put the output in out variable after 10 nanosecond. First of all, why do we need these delays, right? As I explained in gate level modeling, these delays are used to emulate the real world situations, because in real world there is always a delay exists. So you want to emulate that kind of behavior in your circuit or design as well. So that is where the delays are very, very helpful. So once we know what is the use of delay, we will start using the delays in our design, because it will be a realistic design. So in this case, let's take my input is varying like this. Input 1 is varying like this. So this is in 1, and this is time axis. This is at 0 nanoseconds. Let's say this is at 10 nanoseconds. This is at 20. It can be any time period. I am using nanoseconds, but it can be any time unit. Let's say this is 60, 70, 80. Let's say this is very small time period. Let's say this is 82 nanoseconds. Only 2 nanoseconds the pulse is applied. 82, and it is going like this. And my into, let's say, is looking like this. It starts at 20 nanoseconds. It will go up to. So ideally, what does my output will look like? I am drawing the ideal output. If you have inputs like this, right? So this is 10, 20, 30. This one is 60. This one is 80. Right? Ideally, what it will do, whenever there is change in 1 and in 2, immediately it will assign, right? If you don't assign any delay, let's say my assign statement is like this: assign out is equals to in 1 and in 2. Then it will check the inputs in 1 and 2, and it will perform the AND operation. 0 and 0 is 0, and 0 and 0 is 0. 1 and 1 is 1. Up to here it will be 1, and after this it went to 0, because in 1 is 0, and after this it went to again 1, and it will be like this, right? So this is the ideal output, because we are not assigning any delay. But what if we assign a delay? The output will look like this. Since we have assigned a 10 nanosecond delay, 10 time unit delay, no matter what will be the inputs, the output is in high impedance state in the first high impedance or unknown state in the first 10 nanoseconds. After this, it will calculate the values of 10 nanosecond at in1 and in2 are the values at 10 nanosecond of in1 and 2 are 0 and 0. So it will calculate 0 and 0 and then it will assign the output of 0 and 0 is 0, right? Then similarly, there is a change happened here at 20 nanoseconds. So once there is change, it will go to delay delay block and then it will wait 10 nanoseconds. It won't immediately change, but here you see it will immediately change. When there is a change in input, it immediately change. But in this case, since you have added a delay, it will wait for 10 nanoseconds because the delay is 10 nanoseconds. So it will wait for 10 nanoseconds, then it will perform the AND operation between in and into at this particular location. It will take this in one and into, but not this in one and into. This is the thing I want to explain. So this statement will proceed in the order that I explained. Like first step is it will check for the changes in input. Next step is it will go to the delay, and then third step is it will assign the output at that particular location of in and input values. So it will perform 1 and 1 and then it will go to 1. 1.1 is 1, right? Similarly, there is a change is happening here. So at this time period also, my output statement is waiting to evaluate for 10 nanoseconds. After 10 nanoseconds only, it will change, but not here. Ideally, it will change here, right? But we have assigned 10 nanosecond delay. So after 10 nanosecond, it will change and then see it won't take the values of these, but it will take the values of these. So 1 into 0 is my output will go to 0. Okay. Now let's see what happens if the delay is very small. I mean, if the pulse width is very small. So there is a change happened at 80. So my output won't change immediately at 80. It has to wait up to 90 nanoseconds. So this is 90 nanoseconds. It has to wait up to 90 nanoseconds. So it will continue the previous output, whatever it is, while waiting. Once at 90 nanoseconds, it will check the value of here input and input 2. Since both are 0 and 1, it will go as 0. Right. So what happened here? It surpassed this pulse width. Right. We lost this data. This data is lost because my delay is greater than the pulse width. So it doesn't know at that time period what is the changes that is happening in 1 and in 2. Because from 80 nanoseconds to 90 nanoseconds, my output statement is not driving. It is in delay state or sleep state. At this time period, whatever the changes happening inside in 1 and 2 are surpassed. That is what happened here. But in the ideal case, the values are passed as it is, but in the case of delay, it was surpassed. We'll see its advantage once we know what is a race condition and all. But as of now, think like this. If you have a delay that is greater than the, here the delay is 10 nanosecond, which is greater than the pulse width, pulse width of the inputs, the pulse width of the change in inputs. If you have the delay greater than, your delay is greater than pulse width of the input changes, then those pulses will be suppressed or eliminated in the output. This is one of the important feature in Verilog you need to remember. Whenever you are giving any delays, always make sure whether your delay is greater or less than your pulse width, and always make sure what kind of output you want. Based on that, you can define the delay and pulse width of your inputs. This should be very clear, right? Once this is clear, we'll see what is a net declaration delay. So in net declaration, okay, net declaration, there is one more thing, right? Implicit continuous assignment delay. After this implicit continuous assignment delay, we will see what is a net declaration delay. So in implicit continuous assignment delay, what I meant is you can give the delay here itself while defining the net wire 10 nanoseconds out is equals to in 1 plus in 2. So here I am not defining again assign statement, as I have already explained. You can give the delay implicitly while defining the wire. Same thing we have seen in implicit continuous assignment also. The same thing is applicable for implicit continuous assignment delay also. You don't need to define again wire, what is wire out, and then again write assign is equals to assign of 10 nanosecond delay of out is equals to in 1 plus in 2. So you don't need to write two different lines, you can directly write a single line. This is called implicit continuous assignment delay. Now let's see what is net declaration delay. So in net declaration delay, what I meant is you can directly define the amount of delay that this net is associated with. Let's say this net is associated with 5 nanosecond. While defining the net itself, you can define the uh, amount of delay that you want on this particular net. So whenever there is out assignments, assign out is equal to in 1 plus in 2 plus in 3. So in 1 plus in 2 plus in 3. So whenever there is an assign statement, you already defined the delay of 5 nanoseconds. So it will wait for 5 nanoseconds and then it will evaluate the expression. So this is called net declaration delay. While defining the net itself, you can declare how much amount of delay you want, right? The same thing can be applicable in gate level modeling also. In gate level modeling also, if you define like this wire * 50 nanosecond delay of out, you can have and gate level modeling. If you remember how to do the end operation gate level modeling, you will call the Verilog primitives and then we will assign out is equals to in 1 comma in 2. So what does this do? It will perform the end operation after 50 nanosecond delay. This is net declaration delay in gate level modeling, because we are using a Verilog gates here, not the expression or data flow statements, right? So once we have clear cut idea of how to use the assign statement and how to give the delays in assign statement, now we'll see the three most important things in data flow modeling, which are what are expressions, what are operators, and what are operands. So the data flow modeling describes the design in terms of expressions, but not in terms of logic gates, as in the case of gate level modeling. In the gate level modeling, we will describe our design using logic gates, but in case of data flow modeling, we will describe the design in terms of expressions. So what is an expression? An expression is a construct or statement of line that combines the operators and operands. So what are the operators and operand? We'll see in the next slide. First of all, we'll see what is an expression. An expression is a construct that combines operators and operand. Whatever we are doing till now is an expression for output. How we are expression for output is, let's say in 1 into. So this is an expression, or you can write out 2 is equals to in 1 plus into. This is also an expression. It is using operators. These are operators, right? We have seen what is an operator in the beginning slides of the digital design, and then these are called operands. This is an operator which is a symbol, and these are operands which are variables such as net, wire, or register, or any kind of data types, right? So let's see what are the operands. An operand can be any kind of data type such as constants, integers, reals, nets, registers, even vectors, arrays, or even function calls also can be used as an operands. What I meant is, if you want to have a register of ret value, this is my variable, and if you want to have a function call as an operand, you can do like this. My retention value is equals to calculate my odd parity. This is a function that I have defined, user defined function. In this, I want to calculate odd parity between A, B, and C. So this is how you can assign the value into my result variable. Let's say my result variable is using this function as a operand, right? This is an expression in which here the operand is function instead of just a variable. Or you can define like different data types, like let's say I have a real data type of A comma B comma C, and I want my output is equals to A into B into, so this is the multiplication operand asterisk A multiplied by B multiplied by C. So what does it do? It will assign the output of A multiplied by B multiplied by C. So here the operands are real values. Right? So what we have seen what is operand and what is expression. Now let's see what is an operator. An operator acts on operands and produce a desired result. Like we have seen many operators like plus, multiplication, negation, and all. We'll see different kind of operators in the coming slide. There are multiple operators that are available in Verilog, such as these: arithmetic operators, logic operators, relation operators, equality operators, bitwise, reduction, shift, concatenation, replication, and condition. These operators will be very helpful while designing a digital circuit, because they will perform all the logic operations as well as some calculations like multiplication, division, addition, subtraction, and all. So both the arithmetic and logic operations can be performed by using operators. So that is where we can do all the arithmetic and logic unit of any design you want, right? So most of the operators will be working on either two or more operands. The operators that are working on only one operand are called unary operators, right? We have already seen there are three kind of operators, such as three kind of operators: unary, binary, and ternary. The operators that are working on single operand are called unary. The operators that are working on two operands are called binary, and the operators that are working on three operands are called ternary. So whenever the number of operands are one, these are called unary operators, and whenever there are two, then these are called binary operators. Okay. So here this three means it is a ternary operator, that we already seen what is the conditional operator. We will see one more time what is its use.